All right, everyone. How are we doing today? Doing all right? Okay. So, short week this week for us. We have this lecture and the one on Friday. Um, I'm gonna adjust the quiz timing a little bit. Obviously, I adjusted it, and the quiz is due this evening for last week's stuff. Probably what I'll do is give us a little bit of extra time, probably through Wednesday of next week, in order to do this, and then the following week we'll be back on the Monday. Either uh, do Monday or for us here, take a quiz in class. Maybe we'll have a paper quiz to break up a little bit of what we've done in chapter 15 here. Okay, so the somewhat convenient thing about the schedule this time for this chapter is these two sections kind of form a small unit for themselves. So breaking it up and having this be a standalone week won't be so bad. We'll have today's lecture where we're talking about applications, and then Friday's lecture where we're going to be discussing a particular type of integral. It's still a double integral, but it has a specific set of applications, and we'll return later on. All right. So the book covers a handful of different types of applications here. I'm going to list them out. I don't know if I'll have time to do examples for each of these today, but in the online notes, each one of these is covered. So there's an opportunity to check that out. Okay, so the first one is going to be density and mass. All right. The second one is going to be center of mass. The third has to do with moments of inertia. The fourth, probability. And number 5 here is expected value. Okay. Just to make things a little bit clear here, these first 3 and these last 2 are kind of grouped together. All right. There's not a lot of there's differences between these things, but the first one is attacking kind of the physics idea of looking at density and mass and a couple of other properties that are related to an object's density and mass in center of mass and the moment of inertia. And the bottom 2 are statistical properties. Okay. One, how do we measure the probability of an event occurring in the region? And then another one is an expected value, which is a specific type of probability measure. Okay. So just kind of keep that in mind as we go through. Let's look at what it is we're doing here. Okay. So for the first example, all right, this is going to be related to problem types that we looked at back in Calculus 2, but we're going to be doing things in a different context here. Okay, changing some of the rules. If I have some region, okay, I'll draw this a little better. Okay, I have some region here, and what I'm interested in is looking at some small bit here. Okay, this would be the region that would be designated as dA if I'm integrating, right? It's some infinitesimally small region. I choose a sample point inside of that part of the region, and we set up our integral and do all of this stuff. Okay. Call the region D for domain is what we're going to have here. Now, the thing about this Okay, we're going to treat this as something called a lamina. All right. A lamina is a thin material. Okay. In Calculus 2, you did problems like this where you had your lamina, and the assumption was that the lamina had uniform density. Okay. We're tossing that assumption. All right. I don't know if it's come up yet or not, but when I write the Greek letter rho, I write it like this. Okay. Sometimes it looks like this when it's typeset. Okay. It looks like a not quite P. All right. Um, I try to make it mine fancier so it's clear that I mean the Greek letter rho, but that's what it is. So rho is a typical choice of letter when we're talking about density. This is kind of something that the math and physics and generally scientific communities have agreed upon. Okay. So if you see rho and the context makes sense for rho to mean density, that's probably what it means. Okay, just like we use v for velocity and p for momentum and that kind of stuff. Okay, so rho of xy is going to be a density function. And what we can do is if I integrate over a rectangle containing this density function, I will get the mass of the lamina. Make sense? So that's what we're doing here. So the mass is equal to the double integral over d of the density function dA. Okay. Now, for those of you who are engineering people, all right, this idea of lamina is important because lamina are used to generate laminates, okay, which are extremely important materials that we use for manufacturing and engineering, okay. Composite materials that show up to do things like construct airplanes, to make airfoils, lighten things, have special properties and stuff, are often made by stacking thin sheets of these materials on top of each other and using that to manipulate the materials properties. Okay, that's one of the things that they do over at NIAR is construct and test these things so that they have exacting parameters on what the performance and wear properties of a bunch of these specially designed materials are. Okay, they have a whole lab over there that does that. Okay, so if you get a job as an undergraduate or something, that might be one of the things you get hired to do. Okay, it is also how we create microprocessors. Okay, we all have these little smartphones in our pocket. Okay, that are millions of times more powerful than the computers that we use to land on the moon. All right. The way that we make them is by laying down layers of material, one layer at a time, and pressing circuits in between them. Okay. And right now, we just kind of stack them up as silicon wafers. All right. But those wafers can be thought of as lamina. All right. So understanding how this all goes together is the first step at doing cutting edge material science. All right. So this basic type of integral, or this type of integral is going to form kind of a basic piece of the next couple of applications that are related here. All right, so if we borrow an example from the textbook, we want to compute the mass, all right, and we're given this picture. Did not sketch that well. Okay, this here is the 0.11. Up here we have 1. Down here we have 1 as well. This is the line y equals 1 minus x. Okay. All right. So we have this region here. Okay. Now, there are two types of applications that can be thought of both as this sort of integrating density to find mass type expression. Okay. Okay. So here we want to do is we want to find the mass of this shape over region D with a mass density function given to us by rho equals xy. The other version of this problem is an E&M problem, which is find the total charge Q over D with charge density function and this is a lowercase sigma. Okay, this is going to be the same problem. All right, the math is the same. So you can be asked to find total mass or total charge, and you will be given either a mass density function or a charge density function. Mass density functions use rho usually, and the charge density functions in the textbook use sigma. All right, so we'll do the second one, but it's going to be the same type of expression. So capital Q is equal to the integral over D of our charge density function. All right, and it is our job to write this as an iterated integral. Okay, the way that the picture has been drawn, we've set things up so that it's a type 1 region because this top part is y equals 1. Okay, there isn't anything stopping us from doing the problem the other way. As a type 2. Okay, it will work. We get the same answer. We have to, right? Fubini's theorem. But we'll do it the way that it was originally set up. Integral from 0 to 1, integral from 1 minus x to 1 of xy dy dx. I have to fight my very strong instinct to skip steps here. But it's bad. It's bad for me to do that. Okay, so we rewrite things as an iterated integral so it's clear how everything is separated. Now we can do the interior integral. X is a constant. There are many ways to write this expression, but we have xy squared over 2 here, increase the power by 1, divide by the new power for y, which is what we're integrating with respect to. We're going to evaluate y from 1 minus x to 1. We have a dx on the outside here. We have x, and then we can write this as x over 2. Here we're going to have 1 squared minus 1 minus x quantity squared. Okay. Now what we want to do is go ahead and expand that expression. So we're going to have 1 minus, I'm going to write the second part in parentheses, 1 minus 2x plus x squared we all believe. All right. So now simplifying this, we're going to get 1 minus 1, which is 0. We're going to get 2x minus x squared here, and then have this. Right? Okay. So for the next step, I'm going to pull that 1/2 to the outside. We're going to be left with the integral from 0 to 1 of 2x squared minus x cubed dx. So distributing the x and then pulling out the 1/2 because it doesn't need to be in our way. And now we can integrate these other aspects term by term. Increase the power by 1, divide by the new power. Increase the power by 1, divide by the new power. Evaluate from 0 to 1. Both of these have x, so if I plug in 0, I'm just going to get 0. And if I plug in 1, we're going to get 2/3 minus 1/4 here. Okay. We do the necessary scratch work in order to get this to be a common denominator. Multiply the first one by 4/4, the second one by 3/3. All right, leaves us with 5/12. All right, and then 5/12 times 1/2, 5/24. Okay, so fairly straightforward. All right, none of this was hard. There's just a lot of stuff to keep track of, right? One of the things that you should keep in mind as you're practicing and developing your skills and everything for this course is that there's a very big difference between things that are difficult and things that are tedious. Okay, there's a tendency to conflate these two things. All right, don't fall into that trap. All right, I know that there are a lot of annoying things to keep track of, and there was a fair amount of bookkeeping in that otherwise simple problem because it was just integrating a polynomial, right? That's just how this class is. Okay, there's a lot of stuff to do. We're going to be integrating with respect to 2 or 3 dimensions at a time. All right, the important thing is that you practice and develop the mental separation necessary to understand and work with only the thing that matters in that moment. Okay, in this previous problem that we just did, okay, we were doing stuff with y until it was time to do stuff with x, right? You have to just handle that, you know? And that's kind of the trade-off here, all right? We might only get 2 or 3 problems, but each of those 2 or 3 problems are going to be somewhere between 2 to 4 Calc 1 or Calc 2 problems, right? That's how it goes. All right. Okay. So the next part here has to do with moments and the center of mass. Okay. We're still talking about lamina. And the idea is that if I have some shape here of non-uniform density, okay, so here this is a lamina. It's flat, but across its body there might be variations in density, okay? Somewhere along here there is a point where if I place a fulcrum here, okay, it would balance on this point. All right, this point here should be the center of mass. Okay, they've been around for a very, very long time at this point. All right, and so I assume that most people here have seen. I'm going to do my best here. The bird toy that looks like this, that balances on the beak, and it balances well enough that you don't have to have a sharp point here. You can just kind of sit it on your finger. All right. The wings are put up this way like that to balance out the mass, to make it to where the center of mass for this object is concentrated here. Okay. So it's the same kind of idea. All right. The way that this works mathematically is we have some shape. All right. And for the shape, have some region here. Okay. And what I want to do is I want to compute the moments of this. Okay. The way that this is written is having an overbar for x here. Okay. The overbar is an indicator of the fact that the average of the mass in the x direction is going to be concentrated at this particular value. Okay. And the formula for this is the moment about the y-axis divided by the total mass of the object. Okay. And the integral here is given like so. Okay, so I have x times the mass density function. Okay. We have a similar formula for y. This is the average of the masses in, if we're thinking about this in terms of the y-axis. Okay. Now, these formulas you saw back in calculus 2. All right. The thing is that they're actually much easier to deal with if we think about them in terms of double integrals than if we think about them in terms of the way we had to deal with them in Calc 2. Okay, as we had to change everything to be a function of x. It was a big pain in the rear. All right, but here we know how to integrate with respect to both x and y, so we can just do it that way. All right, so this is actually better. All right, there's less to think about. All right, now these terms here, this m sub y and this m sub x, are known as the first moments. All right. And these moments have to do with rotation about the axis. Okay. Basically, going back to this picture here, okay, is in a one-dimensional case, if you have something like a seesaw or a teeter-totter, and the way that you pronounce that has to do with what part of the continental United States you come from. If you place a mass here and a mass here, the lever arm generates a force, right? Okay. The further away from the fulcrum, the more of a twist that is introduced by the gravity acting down upon that element, right? Okay. When we talk about the moments in the context of this problem, it's the same kind of thing, all right? I'm imagining a rotation's happening here around the x-axis, okay? And each point of mass here, depending on what's going on with the density function, forms the same kind of lever that I had in the teeter-totter picture, okay? And we also have the same kind of thing happening with respect to the y-axis, where we're trying to rotate this way, all right? The center of mass is going to be a point in this region where if I gave an equal amount of force to the force being generated by mass and gravity, okay, and I applied that force to that single point, no rotation would happen. All right, an equal and opposite reaction, right? So it allowed me to hold this up, just like happens with the bird here. Okay, if you place your finger underneath anywhere other than this point, it falls over. All right, but if you counteract by applying a normal force, which is equal and opposite to the weight of the bird, then it balances, right? Okay, so that's what this is. You have an example. All right. I'll draw the picture here in a second. D is bounded by y equals 0, y equals 2x, and x plus 2y equals 1. Okay? We want to find the center of mass. When the mass density function equals x. Okay? So we have y equals 0 as one of our boundaries. Okay? We have y equals 2x as another one of our boundaries. Okay? And then we also have this as our third boundary. We put this in the slope-intercept form. looks like this, right? Okay, and depending on how this scaling is done on this picture, looks something like this. Okay, so our region D is in here. All right, again, just this is a quick sketch. There's a more delicate way to do this. All right, but we need our bounds. Okay. So we need a 2x to equal this. That's going to be this point, right? Okay, the fact that it's at 0, 0 is pretty obvious, and we just need one more. So we multiply both sides by 2. Sorry, what am I doing here? Multiply both sides by 2. That makes more sense. All right. X equals 0.2 here. All right. Now, looking at this picture, life is easier if we treat this as a type 2 region, right? The way that we drew it is as a type 1 region, or at least these equations, the way that we're using them so far is as type 1. If we do type 1, what we would have to do is do 2 problems. I'd have to do this type 1 region, then this type 1 region. And 0.2 here for x would be the place where I break it up into 2 different iterated integrals. Right? I don't want to do that. Okay? So it's better if we go this way. All right? If we do that, then this equation here becomes this. That's over here. All right? And this equation becomes this. Make sense? Okay. This is 1 because if I plug in y equals 0 to this equation, I get x equals 1. Right? That's where these 2 lines have to intersect. Okay. And then up here, we figured out that x is equal 0.2. So it has to be 0.4, right? Because it's y over 2 and I multiply by 2. Okay. So that sets us up. We can now find the mass. We're integrating from 0 to 0.4 and from y over 2 to 1 minus 2y of x dx dy. I'm sorry, what? Yeah. This is type 2. We're going this way. Okay. Now, we're doing mass first because we have to do the mass in order to find these values. Okay, so I have to know the total mass first, and then I do the integrals for the moments. All right, so we've written everything out. Get everything set up here. We get x squared over 2 evaluated from y over 2 to 1 minus 2y. So we're going to have a 1/2. I'm going to take the 1/2 all the way to the outside. And then on the interior here, I'm going to change my grouping symbols so that they're more clear. But if you just want to use a bunch of parentheses, that's fine. So it looks like this. Okay, we factor out a 1/2 just because it's in the way. All right, and then I'm left with the other stuff where my expressions for y are getting squared. Okay, a little bit of algebra to do. We can actually take that 1/2 all the way to the outside. Okay, we expand the expression. We have values to look at now. I see I can combine like terms. 4y squared minus 1/4 y squared is going to give me 15 y squared. And now we're ready to integrate with respect to y. Increase the power by 1, divide by the new power. 5 divided by 3, or 15 divided by 3 is 5, pardon me. Okay, and then we plug in all of our values. Okay, it's probably easier if we think about 0.4 is 2/5. And then we can put all this in here. If I plug in 0, I'm going to get 0 because all of those terms have a y in them. So we're going to get 2/5 minus 8/25, because 2/4 squared and then times 2. And then we're going to have 2/5 cubed. So that's going to be 8 over 125. Okay, and then we simplify. So we have deal with the last one first. Okay, so we lose a factor of 5 and then a factor of 4 here. So 5, we're going to have 2 25ths here. Wait, what did I do wrong? No, that's right. Make sense? Okay. All right, then we combine like terms. We can write this as 10 25ths. Ten minus 8 is 2, plus 2 is 4, divided by 2 is 2. Okay, so this is what we have for our mass. Okay, the next step of the problem here, okay, is now this is just a number, all right, that we have that goes out in front of our integral, and we perform a very similar integral with just a slightly different integrand. So for the next part, if I wanted the x value here, it's just 1 over m times the double integral over d of this. And so for our case, it's going to be 25 halves because it's the reciprocal of the mass that we just calculated. And then we do the same integral again, except now there's an x being multiplied times our density function. Okay, the setup is the same stuff. All right, so it's the same kind of problem. All right, so to do y, same thing. I'm gonna leave that aside. Okay, and there are two other types of examples that I don't have time to work through, unfortunately, full on. So I'm going to reference the online notes here so that we kind of see how this this all goes together. All right, and then the example that I just did, by the way, is worked out in the notes, so you can see what the rest of that looks like. Okay. In addition to talking about center of mass, and we've talked about how that looks like from a perspective of the physical interpretation of balance, right? And where the center of mass is and how we interpret that. There's another related idea called the moment of inertia. Okay. The moment of inertia is the rotational analog of mass in the context of like angular momentum. All right. We've all had the real life experience of understanding that there are some things that are harder to spin than others, even if they have the same amount of mass, right? It depends on how that mass is just distributed, okay? There are things that we can use as tops, okay, like the children's toys that we spin on the table, okay, that work nicely, all right? And there are things that we don't spin, okay? There's a reason why the tires on our car are not square, all right? They're round because they rotate better, right? And we may have had the experience, if we've done enough driving, of our car not acting right if our tires aren't balanced properly. Okay, might get some extra road bumpage. Okay, I don't know if anybody have like I have heard the noise of the ding that you get when one of the balance weights thrown off of your tire. Okay, so that's what those random noises are sometimes, by the way, is if you just get your tire balanced, then they didn't use enough stickum to keep the stick weight on there. Anyway, we can also look at what's going on with rotating lamina and determining the moments of inertia for these types of objects, okay? And the formulas are extremely similar to the ones that we had for our first moment having to do with center of mass. There is a second moment, which is the same formula, except now it's the second power. Okay, first moment, first power, second moment, second power. Very easy. Okay. How the only differences between these problems is how difficult these things are to integrate. Okay. And there is 3 types of second moments that we're interested in. The moments have to do about the x and y axes. It works in this rotational orientation idea that I had mentioned before. Okay, that's what we're worried about, is this idea of spinning the lamina around one of these axes. And if you add together the moment about the x-axis and the moment about the y-axis, you get the moment about the origin, which is typically the one that we might use for some physics applications, right? So, but in terms of doing the computation here, all relatively straightforward. No new math. Okay. Our other applications have to do with probability. Okay. When we are talking about probability, we are measuring a function, and that function represents the set of all possible outcomes, the likeliness of all possible outcomes. All right. We believe in something called the conservation of probability. Okay. Much like the conservation of energy or the conservation of mass, we cannot create or destroy probability. All right. There is a set of events, and if that is the set of all possible events in a particular circumstance, one of those events must occur. So if we integrate over all possible events, the probability that something happened is 1. Okay? We add everything up. All right? Now, it is the case a lot of the times that probability is talked about in percentages. All right? 1, of course, is equivalent to a 100% chance. All right. Please keep that in mind if somebody talks about a percentage probability, that you need to convert it to an actual number and do your math in terms of decimals. Right? Don't forget and have an extra factor of 100 floating around for not a not helpful reason. There's a minus sign that should be here. Sorry. Okay. The probability of an event happening in the range of a and b is given by the integral from a to b of f. Okay? This number will be less than or equal to 1. Because if I integrate over all space, I get 1. In talking about events in multiple connected events, all right, the way that we handle that is by doing a double integral. Okay? So x and y are 2 separate events that are controlled by different variables. And what we are interested in statistically is what is the likelihood of both of these things happening? Does x happen and y happen? Okay. Or if I'm looking at event x in a range of values from a to b, and an event y in a range of values from c to d, what is the likelihood that they both occur? Okay. If we do this, we get a function of both variables. This is known as a joint density function. Okay. And it must have the property that the integral over all space of this joint density function is equal to 1. Because if I multiply two numbers that are less than or equal to 1 together, I get a number that's less than or equal to 1. Okay. If we're looking at expected values, it turns out that the formula for this is exactly the same formula as the first moment. Okay? And what the expected value is it is the average value that we would expect from an event occurring in a particular range. Okay? So if our event is rolling two six-sided dice, the expected value is 7. Because that is the most likely thing to occur, right? And you add up all the probabilities that you get for all the other values, right? You add up the 1 time you can get 2, the 2 times you can get 3, the 3 ways you can get 4, the 5 ways that you can get 6, the 6 ways you can get 7, the 5 ways you can get 8, the 4 ways you can get 9, the 3 ways that you can get 10, the 2 ways to get 11, and the 1 way to get 12, right? And then the average of that is your expected value. It's just that we're measuring these averages now using integration as opposed to doing it like computing an average. Okay. Anyway, so that's what's going on here. There's a couple of examples to look at. There are applications to this in terms of physics as well, because we can only statistically determine the likelihood of where a particle lies. And all of this is handled using this very powerful tool that we have now introduced and understand. All right, enjoy it, everybody, and I'll talk to you next time.